The human brain has 100 billion neurons, and each of those neurons is connected to 10,000 other neurons. Sitting on your shoulders, these shoulders, and all the other shoulders in the world is the most complex object in the entire known universe. If you know me, you know that I'm obsessed with the brain. And I'm also really obsessed with outer space. So when I heard about these star-shaped cells called astrocytes, I was, once again, obsessed right away. The brain functions on two units of life, neurons and glia. Neurons are nerve cells that send and receive electric signals throughout the body through something called synaptic transmission. Glia, or glial cells, are non-neuronal cells that don't fire action potentials, so they don't communicate through synaptic transmissions like neurons do. Astrocytes, also known as astroglia, are a subtype of glial cells shaped like stars. We know a little bit about them, but much like the brain, they're pretty much all unexplored territory, which is yet another similarity to the vast universe. What we do know about astrocytes is that they serve many functions, including the biochemical support of the cells that form the blood-brain barrier, which is the protective layer around the brain. They also help providing nutrients to the nervous tissue of the body, and they maintain homeostasis of ions and blood flow. While doing all these amazing tasks, astrocytes also play a role in repairing and scarring brain tissue and the spinal cord after infections and injuries. They're literally always on the grind, like always. Okay, now to another amazing, super cool topic, optogenetics. Optogenetics is this method of brain research that allows for the precise modulation with light of neurons or neural populations that have been genetically modified to be light sensitive. So in layman's terms, you're essentially controlling the brain with light. Optics-based astrocyte experiments or optics-based approaches are better for astrocyte research than the typical electric stimulation-based experiments because optogenetics is less invasive and it also has precise spatial resolution. It also offers the ability to control both neurons and astrocytes at the same time, like with real-time control. With optogenetics, channels can be targeted to specific cell types and we can manipulate the activity of singular cells. Astrocytes are hypothesized to be linked with neurodegenerative diseases, specifically that astrocyte dysfunction could be linked to the presentation or mechanisms leading to the pathological changes in CNS tissue or central nervous system tissue. In patients with neurodegenerative diseases, astrocytes often show deficits in communicating with brain cells as well as displaying abnormal morphology. So with this figure, it displays how astrocyte pathology gets changed in the presence of the developing neurodegenerative disease. So figure A shows astrocytes communicate with neurons through a triple synapse method. So we can see that there are two synapses and then there's an astrocyte that kind of covers them both. Astrocytes are atrophic and therefore reduce coverage of the synapses in the early ages of neurodegenerative disease development. So we can see that in figure 1b, where the astrocyte coverage has reduced and therefore the synapse is more exposed. In figure C, we see that in the late onsets of these diseases, an event called reactive astrocyte proliferation occurs. The astrocytes enlarge by a significant amount and their morphological complexity reduces. And this results in glial scars, which prevent the transmission of nutrients from the astrocyte to the synapse, but they push the release of neurotoxic factors which often induce the death of neurons. These experiments indicate a close relation between astrocyte proliferation and the pathological processes in neurological diseases. Therefore, optogenetic modulation via actuators called channel rhodopsin or archaerhodopsin targeting astrocytes offers a possibility to treat neurodegenerative diseases by addressing astrocyte and neuron communication. Epilepsy is a neurological disease that impacts about 1% of the world's population. And while that might not seem like a lot, that is about 70 million people. Although the cause for epilepsy isn't that well known, it is widely agreed that it's related to an issue between the balance of inhibitory and excitatory neurons in the brain. In epilepsy, the balance between excitatory and inhibitory neurons is lacking due to a dysfunction of principal or the dysfunction of interneuron, and interneurons in this scenario can be referred to as the astrocytes. Due to the way that optogenetics works, it's technically possible to control individual neurons to stop the effects of epilepsy. So if we take a look at this figure, we can see a principal neuron with hyperexcitation. And the second figure, or figure A2, portrays a halorhodopsin, which is another actuator, targeting principal neuron. Halorhodopsin is a light-sensitive chloride pump which is used to inhibit neuron activity in optogenetic experiments. When the yellow light shines on the neuron, the chloride ions enter the neuron, and then they hyperpolarize and inhibit the generation of an action potential. They basically don't let the neuron communicate through synaptic transmission. Figure B1 displays an astrocyte or an interneuron synapsing or communicating with a principal neuron which is currently hyperexcited. Figure B2 shows channel rhodopsin, which is the actuator that we discussed earlier, being targeted to the astrocyte. Channel rhodopsin is a light-sensitive ion channel used to stimulate neuron activity in optogenetic experiments. So this is kind of opposite to halorhodopsin, which inhibits neuron activity. Channel rhodopsin activates neuron activity. When the blue light illuminates, channel rhodopsin allows sodium, hydrogen, and calcium ions to enter the astrocyte. This depolarizes the cell membrane and it stimulates the generation of action potentials, which leads to the release of gamma-aminobutyric acid, also known as GABA, which then suppresses the action potential of the principal neuron. In both of these cases, the principal neuron, or the neurons triggering the effects of epilepsy, would be inhibited, and the communication necessary to start an epileptic response wouldn't happen. So what's in store for the future? As cool as optogenetics sounds, and I know it's super cool, there are a significant number of risks in optogenetic treatments that need to be overcome. Optogenetics requires light, which generates heat, and this heat could potentially damage neural tissue. But there are a couple ways to reduce this risk that scientists are working on right now. One, we could improve membrane expression of optogenetic control mechanisms for their photocurrents. Through this, photocurrents could be activated with lower light intensity or lower light power density, and that would reduce the amount of heat, therefore reducing the risk of damaging neural tissue with heat. The other potential way to get around this is to develop or find new actuators that are red-shifted. Red light penetrates neural tissue easier than the typical blue light that's most often used in experiments today, due to its absorption by hemoglobin, myoglobin, and lipids. It's also more precise than blue light. Therefore, if we end up finding actuators that are red-shifted rather than blue-shifted, we would get the same result with less light power. As I said, although there are a few pretty large implications to using optogenetics for astrocyte research right now, we've basically confirmed that it's an extremely powerful tool for the task at hand. That pretty much sums up what I had prepared for this video. If you liked it, and I really hope that you did, give it a like and maybe subscribe. And if you want to read about these experiments that I wrote about more in depth and with more of a technical explanation, I will link the article in the description so that you can go read that on Medium and maybe give it a few claps there. And that is how the universe and the brain collide to save lives.